Hello AP Physics 1, it's Mr. Ng with a short lesson on Newton's second law. In this lesson, I'm going to go through those classic elevator problems that you see a lot in AP Physics. And really the big ideas of this lesson is number one, sum of forces, meaning we're going to do a notation where we do sum of forces equal to something and something, right? Whatever it is, whatever you get from your free body diagram, and it's going to equal to 0 if it's staying still, or the sum of forces is equal to blah, blah, blah. Whatever is in our free body diagram is equal to MA. But you'll see that when I get through some sample problems. On top of that, we're going to talk a little bit about normal forces and apparent weight. Meaning when things move up, we have the regular weight. mg is our regular weight. But we have what's called our apparent weight, which is the normal force. When things move up and down, they don't weigh the same. In order for Newton's second law to be satisfied, as things move up and down, their apparent weight changes, right? But it doesn't mean that their actual weight changes. Just because you're moving up and down doesn't mean, it doesn't mean I no longer weigh 150 pounds, right? As I move up and down, I'm still 150 pounds, but if I was standing on a scale, that thing would change. It'll make more sense once we start digging into some problems. Let's do a classic elevator problem. This one is called apparent weight loss, and that's what we're going to cover on this slide. We're going to cover apparent weight versus regular old weight. So a 65 kilogram woman descends in an elevator that briefly accelerates at 0.2 g, meaning 20% of gravity, meaning 1/5 of 9.8. Downward when leaving a floor, she stands on a scale that reads in kilograms. During this acceleration, what is her weight? So that's part 1. And what does the scale read? That's part 2. Before I do too much, let's do a free body diagram. So part 1 of any of these types of problems is to make a free body diagram. So here we have the woman. Only 2 vectors on her. She has a force down and she has a force up. And on normal circumstances, these 2 vectors should be equal in magnitude. If she was staying still, this would be equal in magnitude. But because she's going down, that means the difference in magnitude should equal this acceleration going down. Meaning the magnitude up should be just a little bit shorter. How much shorter? Exactly this much shorter, right? But I'm getting ahead of myself. We'll talk about that when we do Newton's second law in a bit. So first and foremost, let's label our vectors. This is mg, which is the weight, right? Your weight is mg. That's it. The vector up is the normal force, and the normal force is not the weight. It's something called the apparent weight. The apparent weight is the weight that you inflict on the floor, on the scale, right? This little normal force, look at this diagram, right? This is the F of n. This is the apparent weight. Meaning as you move up and down, your effect on the scale, right, according to Newton's third law, changes to so that the sum of forces balance out. I know that sounds a little bit confusing, but just memorize mg is always weight. But as you move up and down, you make something called an apparent weight. So when you move up and down, if you're on a scale, the scale looks heavier and lighter. Okay? So let's do Newton's second. That's part 2. Oh wait, I forgot to just give you the weight. The weight is easy. Part 1, the weight is mg. mg means 65 kilograms times 9.8 meters a second squared. That means our weight is 640 newtons. If you want to put it in kilograms, you just kind of divide that by 9.8. Or you could also say 65 kilograms if you want the weight in kilograms. But technically, weight is a force, so it's better to express it in newtons, FYI. Okay, Newton's second. Let's do part 2, right? What does the scale read? Meaning we need to solve for this normal force. what does the scale read? So let's do sum of forces. The sum of forces is equal to, and then let's do the positive ones first, which is going to be the normal force minus mg, right? Mg is going down, that's why it's negative, right? Right here, it's negative. Mg is going down. Is equal to, look what I'm going to do, negative m times a. It's negative because the acceleration is going down, so I know it's negative. It's important to keep the signs consistent when we do these little elevator problems. Normal force is going up, mg is down, acceleration is down. Positive, negative, negative. Good. So now all we got to do is solve for n. I don't need to worry about the sum part. It's just kind of a convention that it's there. To solve for n, I'm just going to add mg on both sides. And early on, you're going to feel a little bit uncomfortable doing this weird math with just the letters, but you'll get used to it. So that means normal force is equal to positive mg minus ma. Great. The normal force is equal to m times g minus a. Now let's plug in. That means the normal force is equal to the mass times gravity minus our a is 0.2 g minus 0.2 g, right? 1 minus 0.2, meaning n is equal to m, the mass, times 0.8 g, meaning she's going to weigh 80% of what she actually weighs, or her apparent weight is 80% of her real weight. So let's plug it in. That means the normal force is 65 kilograms times 0.8 g, or if you just multiply 0.8 of 65, 52 kilograms times g, right? So she's going to look like she weighs less, and we already talked about that, right? She's going to look like she weighs less, just a little bit less, and it looks like she's going to weigh 52 kilograms, okay? So what did I do? Number one, I did a free body diagram. Number two, I did Newton's second law. I did what's called a sum of forces. And then I just kind of did a little bit of rearranging until I got to the actual mass. Good? Okay. Finally, part B. What does the scale read when the elevator descends at a constant speed of 2 meters a second? Well, it's a constant speed. That means this is in dynamic equilibrium. That means sum of forces is equal to, 0. That means she's going to read 65 kilograms again, right? There's no, like, if we had to do the sum of forces is equal to normal force minus mg is equal to 0. That means the normal force is equal to mg. Easy. Good? Let's do this sample problem again, but this time, instead of the a going down, let's assume that the acceleration is now up. So instead of 0.2 g downward, it's going to be 0.2 g upward, okay? And I think the most interesting part is, of course, finding what the scale reads, or finding the apparent weight. So let's start with the classic steps. We're going to start with a free body diagram, the FBD. We're going to draw the woman. This is not the elevator, FYI. If this was the elevator, we wouldn't be dealing with mg and normal force. We'd be dealing with tension, right, and mg, right? But we're not dealing with the elevator box itself. We're dealing with the woman, a different system. And for the woman, she has mg down, and she has normal force up. And for us, we're going to have a total acceleration up, some sort of a up that's this time 0.2 g, meaning the sum of these forces need to be up. That means this is going to be a little bit higher up. So what used to be the same is now a little bit higher up, so that the total sum, when these two things cancel out, this is going to be equal to that. Okay, so what is the total normal force now? Well, let's do some sum of forces. Sum of forces. So that means the sum of the forces is equal to, again, I'm just going to go with positives and negatives. Normal force, that's the positive, minus the mg. And then let's go with is equal to, and this time I'm going to do a positive ma, m times a, because it's positive, it's going up, right? So that means n, the normal force is now, I'm going to add mg on both sides. All right, so n, normal force is now mg plus ma. That means normal force is equal to m times g plus a. That means the normal force is now m times g plus 0.2 g. The normal force is now 1.2 of the mg. So now she's a little bit heavier, 20% heavier, okay? So if it's going up, if it's going opposite the mg, we use this formula. Up, we're using m times g plus a. Notice that if it's going down, on the last problem, it was m is equal to g minus a. If you just memorize that, that might simplify things for you. Good? To sum up, there's a difference between mg and apparent weight. Mg is the actual weight, while the normal force is the apparent weight, right? Meaning as you move up and down on an elevator, you would have different readings on a scale. If you're going in the direction up, you're going to feel a little bit heavier. If you go the direction down, you're going to feel a little bit lighter. And there are some summative equations here. If you're moving up, your normal force or your apparent weight is equal to mass times g plus a. If you're moving down, you're going to weigh a little bit less. So your normal force or your apparent weight is going to be m times g minus a. Okay? M times g minus a versus m times g plus a. When you move up, you're heavier. When you move down, you're lighter, right? Which is why you go to Magic Mountain and there's those big drops. For a moment, you feel weightless. Or astronauts in space, they're constantly free falling, so that's why they feel weightless. Good. Thank you very much for watching.